Hello students, welcome you all to another new video of our channel. Where we are going to discuss about optical fiber. In this video, we will discuss about what is an optical fiber, what are the different sections or different parts of optical fiber, how it works, what are the different types. Also, we will discuss about the different applications of optical fiber. In day-to-day life, you can see optical fibers are nowadays used everywhere. Optical fiber is nothing but a waveguide. You can see it is written here as optical fiber as a waveguide which are fabricated from glass or plastic. Mainly they are made up of glass or plastic operated on optical frequencies, because light waves are used, electromagnetic waves are used. For that reason, that is said to be optical frequencies. Mainly optical fibers work on the principle of, you must have studied about total internal reflection. So total internal reflection, that is a concept of optics, is nothing but the backbone of working of any optical fiber. So optical fiber is a dielectric waveguide which is made up of mainly glass or plastic. It is said to be dielectric waveguide because dielectric means any insulating material, because glass and plastics are insulating material through which light waves are transferred from one point to another wave. So we are going to discuss about in details. So optical fibers are normally cylindrical form, and the three main parts are core, cladding and jacket. From this diagram you can see the central part of the optical fiber is said to be core, then the covering of core is said to be cladding, and the outer layer is said to be protective jacket, or normally it is said to be only jacket. Then what is the difference between a core and cladding of an optical fiber? Why jacket is used? Core is actually the main working function or working region of the optical fiber. Core and cladding both are made up of glass or plastic, but there is a slightly different. Core refractive index, if you write refractive index mu or n also, whatever you can write, the refractive index of core is always greater than the refractive index of cladding. Whenever you will find out, always you will see refractive index of core is greater than refractive index of cladding. Core and cladding both are made up of glass and plastic, but the composition is slightly different, so that the refractive index of the central section or the core section is always greater than that of the cladding. And this protective layer is used in order to protect the core and cladding, because both of them are mainly made up of glass and plastic. So this is just used to protect the core and cladding. So this is said to be the protective jacket, the outer layer. And outer layer is mainly made up of any type of polymer or synthetic material. Clear? So core, cladding and jacket, these three are the three different parts of optical fiber. Core is the central part having higher refractive index. Cladding is the part which covers the core, having slightly different or less refractive index as compared to that of the core. And this is the outer layer which is made up of any type of polymer or synthetic material in order to protect both core and cladding. So due to change in refractive index of core n1, let refractive index of cladding is n2. So always n1 is greater than n2. So always remember, between core and cladding, core always behaves like optically denser medium having slightly higher refractive index, and cladding behaves like optically rarer medium having slightly less refractive index. So here you can see in details it is written about core. So core is the innermost region of the fiber which has specific property of conducting an optical beam, that means the light, made up of glass or plastic. It covers with another layer of glass or plastic whose chemical composition is slightly different. I have told you that refractive index is slightly different by slightly different composition, which is known as cladding. Clear? So next you can see cladding. This is the region just above the core, the outer layer. If this is the core region, then the region which covers the core is said to be its cladding. Refractive index is slightly less. So here it is, you can see here it is written slightly lower than that of the core, and the optical fiber may have an abrupt boundary. We will discuss about what about abrupt boundary and gradually change, that will comes under types of optical fibers. Okay, we'll discuss about that. That depends upon the material as well as the nature. Then this is the jacket. The outermost layer of optical fiber is said to be jacket. It is mainly used to protect it. So this is made up of plastic or special kind of polymer synthetic material. So it is used in order to just protect it from different applications, different environmental causes as well as moisture absorption. Okay, in order to prevent any type of accident, jacket of that optical fiber is always made up of any polymer or plastic. These are the three different parts of optical fiber. So optical fiber always works on the principle of total internal reflection. So let me just slightly introduce total internal reflection. This will be just like a revision for optical fiber for you. So total internal reflection. So total internal reflection means when ray of light travels from optically denser medium to optically rarer medium. So if this is a perpendicular trend, if we draw this as perpendicular is here and this is a boundary. This is optically rarer medium, optically denser medium. So always we know that when ray of light travels from optically denser to rarer, without medium it will travel along the dotted line. But due to the presence of optically rarer medium, always ray of light travels away from the normal. When it travels from optically denser to optically rarer, so it will slightly bend away from it. So then if we increase the angle of incidence, if the angle of incidence is here I, but if we increase the angle of incidence, I is greater than IC. What is IC then? IC means the critical angle. That means the angle of incidence, for which angle of refraction is 90 degree. 90 degree. That is said to be critical angle. I equal to IC. So here if ray of light travels, which is equal to the critical angle for those pair of optically rarer and optically denser medium, then the angle of refraction will be 90 degree. So if the angle of incidence is more than critical angle, if the angle of refraction is more, angle of incidence is more than the critical angle, then the ray of light completely reflected back into the same medium instead of refraction. Since ray of light is completely reflecting into the same medium, this is said to be total internal reflection. So the conditions are the light must be traveling from optically denser to rarer medium, because whenever light travels from optical denser to rarer, then it will bend away from the normal. But when ray of light travels from rarer to denser, it will bend towards the normal. So this is the first condition. And the second condition is critical angle. If we know the critical angle for those pair of medium, then angle of incidence must be greater than the critical angle. So I must be greater than critical angle. These two are the conditions for total internal reflection. One is light must be traveling from optically denser to rarer, and angle of incidence must be greater than equal to critical angle. So now we will discuss about the different types of optical fibers. Optical fibers are mainly divided or classified into two categories. One is step index, one other is graded index. This is on the basis of how the refractive index of core and cladding are varying. Core is having higher refractive index, cladding is having slightly less refractive index. So accordingly, how both of them varies, the refractive index varies between core and cladding, they are said to be step index optical fiber and graded index. From the name, you can also identify step index. Suddenly step, one step is drastic change, suddenly there is a change. When there is a drastic change of refractive index between core and cladding, that type of optical fiber is said to be step index. But when there is a gradual slope, there is a slope of change in refractive index between core and cladding, that is said to be graded index optical fiber. So we will discuss each one of them in details. Here you can see on the basis of refractive index profile, mainly there are two different types. One is step index, another one is graded index. So first we will discuss about step index. So step index means when there is a sudden change in refractive index. For example, we consider the core. This is the core region and this is the cladding region. Okay, this is the cladding region. This is the cladding. Let the core is having refractive index of 1.5 and the cladding is having refractive index of 1.45. So when we'll travel from here, from the center, here refractive index will be 1.5, here refractive index 1.5, here also refractive index 1.5. But when you come to the boundary, at the boundary refractive index, since it is the core region, boundary refractive index will be 1.5. But suddenly if we move from boundary to the cladding region, suddenly there will be a drastic change in refractive index. A sudden change in refractive index, that discontinuity suddenly appears while we travel from core to cladding. This is the reason why it is said to be a step index refractive index. Step index optical fibers, not refractive index. So step index optical fibers are those where there is a step discontinuity between the refractive index, step discontinuity between the refractive index of core and cladding. And here, if N1 is the refractive index of core is having radius A, then beyond A, suddenly we will find out another value. So if you plot the refractive index, then we will find out a graph like this. Refractive index along y-axis, let this is radius, along x-axis. So in step index, if this is the core region, core is having higher refractive index, then there will be a sudden drop. This is the core region, this is core, and this is cladding. In core region, refractive index, whatever the value, that will remain constant throughout the core on both sides. Suddenly, if we move from core region to the cladding region on both sides, you can see there is a step discontinuity. That's why it is said to be step index optical fiber. So, step index optical fiber means when the refractive index of core and cladding region varies suddenly or drastic change, or that value discontinuity takes place suddenly, that type of refractive index is said to be step optical fiber. Clear? This is all about step index. And step index is also of two different types. One is single mode step index, another one is multi-mode. From the name you can also identify single mode. Here you can see it is written, one is single mode, another one is multi-mode. Single mode means this single mode is also known as mono mode. Single, mono is also one. So when one wave or one mode of wave is traveled, that is said to be single mode. When number of waves are traveling, that is said to be multi-mode step index. Clear? Step index means there is a drastic change between refractive index of core and cladding. Single mode means one, that is also said to be mono mode. Multi-mode means number of. So single mode means one. One means when that core region, core diameter or core radius is very less as compared to the cladding. So only one wave will travel through it. Multi-mode means when the core region is wide, that is the diameter of core region is larger, and number of waves are traveling simultaneously, that is said to be multi-mode. So in details we will discuss here. Here you can see it is said to be the single mode step index optical fiber. So in single mode step index optical fiber, the difference between core and cladding is very small. The refractive index difference. And if we plot the graph, for example, this is the total optical fiber diameter or radius, and this is the core. So the core diameter is very less as compared to this is the core area, and this is the cladding area, and that core region is always between 8 millimeter to 10 millimeter, or you can also write down in terms of 8, this is actually 8 micro, milli to micro, in this range. If the width is more, that is in millimeter range, otherwise in micrometer. Mainly it is in micrometer range. Similarly, such fibers are used for communication for longer than 200 meter. Since one wave is traveling, the possibility of loss of energy will be less, because if number of waves are traveling, due to attenuation, more energy will loss, but here less energy will loss. So single mode step index is mainly used for longer distance transfer of energy or transfer of any type of wave. Clear? Then multimode. In multimode, the diameter will be more than that. This will be always you can write down in millimeter, as well as also you can write down in micrometer also. This is more than the single mode. So here if you see the diameter, this is the core region, this is the cladding. This is the cladding region, core and cladding. Clear? So you can also write down in micrometer range. For small optical fibers, these are, you can also write down 20 micrometer to 100 micrometer, then 100 micrometer to 200 micrometer. Average is 125, which is written here also. Okay. The difference between refractive index and core material is kept relatively large, because then we have graded index. So graded index means when the refractive index of core gradually decreases. It has a maximum value at the center. At the center, if we draw a core and cladding, if this is the core and this is the cladding, so here you will find out the refractive index will be maximum at the axis here, maximum. But as we move from core to cladding region on both sides, there will be a gradual change. Gradually the value gradually decreases to the cladding region. Once it will reach here, again here it will be a constant value. So maximum value at the center, then the value gradually decreases towards the cladding, and again at cladding the value remains constant. And obviously we know that the refractive index of cladding is less than that of the core. So that is said to be, since there is a gradual decrease in refractive index, this is said to be graded index optical fiber. So at center it has maximum value. Let this is the cladding region, or this is the core region you can draw. Let this is the core. Then here you can find this is core. This is core diameter, radius along this, the refractive index, and this is cladding. Cladding. So here you can see initially it will have maximum value at the center. As we move on both sides, gradually the value decreases up to a constant value. That constant value is nothing but the refractive index of the cladding. This is the cladding region. This is the cladding region. In core region, there is a sharply fall or gradual fall of refractive index due to change in refractive index. Since the value gradually decreases, this is to be graded index optical fiber. Now we will discuss about the propagation of light through any optical fiber. How light wave travels through any optical fiber, what are the conditions, what are the limitations also that, and what will be the maximum angle with which you can project one light wave so that it can easily travel through an optical fiber due to the total internal reflection. What is the maximum angle? That maximum angle with which one light wave can travel or one light wave can incident on any optical fiber so that it can easily go through it is known as the acceptance angle. Acceptance angle. So acceptance angle means here you can see one light wave is here, one light wave incident on the optical fiber. This is written as theta I. So what will be the maximum value of theta I so that we can introduce one light to this optical waveguide and it will travel through it. So we will find out that. So first you can see here one light wave is striking the optical fiber on its axis, core of the axis at a point A by making an angle theta I, and here it is written theta R, angle of refraction. Again this value slightly bends away from the normal because outside is AR. Let for AR we have written NO. N1 is refractive index of the core, N2 is refractive index of the cladding. Core, cladding are N1 and N2. N0 is refractive index of outside medium, maybe air, maybe water, maybe any other thing. At A it strikes, then it goes towards that point B, and here again it reflects. So first we have to see at point A. At A point. At A point, if we apply Snell's law is sine I by sin r, so I is here theta I divided by sin r, r is here theta r, this angle theta r, this is theta r, equal to refractive index, we know that n2 by n1, refractive index, because from Snell's law we know that sin I by sin r equal to mu2 by mu1. Mu2 means second medium refractive index and mu1 means first medium refractive index. So ray of light is traveling from here whose refractive index is n0 and enters the core region, and core having refractive index n1. So second medium is where refraction takes place, whose refractive index is n1, divided by mu1. Mu1 means where the ray of light travels or incident light, refractive index is n0. So we can now cross multiply. If we cross multiply, we can write down n0 sine theta I equal to n1 sine theta r. This is one equation we get. Again I am repeating, at point A we are using Snell's law. Snell's law is nothing but sine of angle of incidence to sine of angle of refraction is equal to refractive index of second medium divided by refractive index of the first medium. So we use that sine theta I by sine theta equal to n1 by n0. Clear? Then you see this triangle. This triangle. This is 90 degree in triangle ACB. Theta r plus phi plus 90 degree. This is theta r, this is phi, this is 90 degree. Clear? If we add all the angles of a triangle, total will be 180 degree. So directly we can write down 180 degree. So if this is 180, then theta r plus phi, this is equal to 90, or in place of theta r we can write down 90 minus phi. Theta r equal to 90 minus 5 can write down. Here you can see we have sine theta r. So what will be sine theta r? Now sine theta r equal to sine 90 minus phi, and sine 90 minus theta is nothing but cos theta. So you can directly write down cos phi. Now we can modify this equation. If we modify, we can write down n0 sine theta I equal to n1. In place of sine theta r, we can now write down cos phi. Cos phi. We just modified that theta r in terms of phi. So I am writing this equation 2 in next page, which is equal to n0 sine theta I equal to n1 cos phi. We have given it as equation number 2. Clear? This one you can see, equation number 2, n1 cos theta, n0 sine theta I. Our aim is to find out what will be the maximum value of theta I. Now we get n0 sine theta I equal to n1 cos phi. What will be the minimum value of phi? Phi we have taken here, you can see. We have taken phi as here. This is the at point B. At B phi, we get phi plus theta r equal to 90. Clear? In previous page we have written here, you can see phi plus theta r equal to 90. So try to understand one thing. A plus B equal to 90. Clear? Phi is here, the angle of incidence at point B. B is nothing but the interface between core and cladding. In order to do total internal reflection, the angle of incidence must be greater than the critical angle. Critical angle must be greater than critical angle. Phi must be greater than critical angle theta c. So the minimum value of pi must be equal to theta c. If theta c will be there, ray of light will travel like this, perpendicular. So the minimum value of phi is here theta c. So now understand one thing, A plus B equal to 90. If A is minimum, B must be maximum. For an example, if you consider, let phi equal to 20 degree. If phi 20, then theta must be equal to 70. If phi value increases from 20 to now we increase 30, this value we have to decrease from 70 to 60. Similarly, if we increase the phi value to 40, so theta r value we have to decrease again to 50 because both are inversely proportional to each other. A plus B equal to constant. So if theta value decreases, phi value increases. If theta r increases, phi value decreases. So if one is minimum, other must be maximum. Let the minimum value we have considered here theta c. Minimum value is here theta c. Then when phi equal to theta c, then theta r will be maximum. This is the minimum value because A plus B equal to constant. Let the minimum value of phi is, let for an example we have taken 15 degree. We cannot go below 15 degree. If it is 15 degree, then in order to make the result 90, this must be 75. So this is the maximum value. So here we have written for minimum value phi equal to theta c is the minimum value. For minimum value of phi, theta r must be maximum. Clear? If theta r is maximum, these two are, this is angle of incidence, this is angle of refraction. If theta r is maximum, then theta I is also maximum. Let theta m we have written maximum. Then how? Because here at this point we have written sin theta I by sin theta equal to n1 by n2. n1 by n0 is a constant quantity. A by B is constant. If A by B constant, that is directly proportional. If A increases, B also increases. For example, the result we need is 2 and sin theta r, let theta r value we have taken, let this is x by y. So if we put x equal to 5, then y must be 2.5, so that we will get 2. If x equal to 10, this must be equal to 5. So if x value increases, y value increases, directly proportional. So theta I and theta r both are directly proportional to each other. So if one value is maximum, theta r is maximum, then theta I must be maximum. So we get the condition that when phi equal to, the final result we get that when phi equal to theta c, then theta I means this angle, the angle with which the ray of light is projected or incidented on point A, which is the center or axis of that core. Theta I equal to maximum, theta m. We are going to find out here the maximum angle with which we can project one light so that total internal reflection takes place, and this is nothing but theta m, which is said to be the acceptance angle. Now we have to use the value of phi and theta I in equation number 2. Equation 2 you can see n0 sin theta I equal to n1 cos phi. Clear? Now we have to use that here. So once we use in equation 2, we get n0 sin theta m equal to n1. Here you can see cos phi was there. Cos phi, in place of phi we can write down theta c. Cos theta c. Equation number 3. Now we have to see here B, at point B, when phi equal to theta c, then this will be 90 degree. Now we are using Snell's law. At point B, Snell's law, sin I equal to here critical angle divided by sin r. Sin r is here 90 degree because when phi equal to theta c, critical angle of refraction will be 90 degree. This is the condition. Critical angle is the angle of incidence in the denser medium, for which angle of refraction in rarer medium is 90 degree. So we are going to use that value 90 degree equal to second medium is cladding is nothing but n2 by n1, and sin 90 you already know that this is 1, so sin theta c equal to n2 by n1, but we need cos theta c here. So cos theta c equal to 1 minus sin square theta c square root, so we can directly write down 1 minus n2 square divided by n1 square, because n2 by n1 whole square, so you can directly write down n1 square minus n2 square divided by n1. This is the value of cos theta c. Now we have to just use the value of here cos theta c here. So cos theta c equal to n1 square minus n2 square divided by n1. So we have to use that in equation 3. So in equation 3, if we use that, then we will get n0 sin theta m equal to n1 in place of cos theta c. We can now write this expression n1 square minus n2 square divided by n1. n1 square minus n2 square root divided by n1. Now n1 we can cancel here. So this is sin theta m equal to n1 square minus n2 square root divided by n0. This sin theta m is known as numerical aperture. Numerical aperture. Sin theta n, that is maximum value, equal to n1 square minus n2 square by n0 is known as numerical aperture. What is numerical aperture then? Numerical aperture is nothing but the capability or ability of accepting light by the optical fiber. How much light it can accept. Then we have to find out theta m. So theta m equal to just sin inverse n1 square minus n2 square root divided by n0. Clear? So this is the expression for acceptance angle theta m. For air, if the outer medium is air, you can directly write down n not equal to 1. So this will be just n1 square minus n2 square. So by this method, you can derive the expression for maximum angle with which light can travel or light can project it towards the optical fiber, so that it can easily move by doing total internal reflection. This is the expression for acceptance angle, and this one is numerical aperture. Similarly, here is another term is also there, fractional refractive index change. Fractional refractive index is nothing but delta, which is equal to n1 minus n2 magnitude divided by n1. That ratio is said to be fractional refractive index change. Yeah. Next we have some applications. Nowadays optical fibers are used everywhere. So in transmission of digital data, TV, CCTV, remote monitoring, then defense system, then medical field, everywhere optical fibers are used. This is all about optical fibers. Okay, I hope you all understand all this. Thank you.